Hello all, welcome to the webinar series of IEEE MTT AP EMC Joint Chapter Islamabad. I am Dr. Noshirwan Shaib. I am the chair of IEEE MTT AP EMC Joint Chapter. I am also working as an assistant professor at Research Institute for Microwave and Millimeter Wave Studies at National University of Science and Technology, NUST, Islamabad. So today we have a webinar number 10, which is focused on innovative application in health and food industry through 3D microwave sensing and imaging. In addition to today's talk, I would like to mention that today we also have in the worldwide we have the IEEE Day celebration. So it typically happens on Tuesday of every October every year, and this talk is basically embed with this IEEE Day. So let me tell you about the IEEE Day. So IEEE Day, the basic theme of the IEEE Day is to leveraging technology for a better tomorrow, that we should take advantage of the technology and use the IEEE web platform for the betterment of the society. This IEEE Day is celebrated every year on first Tuesday of October. It basically celebrates the anniversary of the first time that IEEE members were gathered back in 1884. And it's been 10 years now that this day is celebrated every year. And this time, unfortunately, due to COVID, everything is virtual. So all the activities that will be happening on 6th of October under IEEE Day are virtual activities. So with this day, we would like to thank the volunteers and IEEE to basically making our life better. The IEEE platform is one of the largest platform that helps community both in technical and humanitarian aspects as well, and to make the life better. So now so now you can also get more details about IEEE 2020 Day on these different social media channels, including Facebook, Instagram, Twitter, and IEEE TV and their website as well. So with this, let me start the initial introduction to the webinar for that we have arranged, particularly on the IEEE Day. So I will start with first my university that I belong to National University in Sciences and Technology, and that university has several campuses across the country in Pakistan, and we are based in Islamabad campus. This is in a bird's eye view of Islamabad campus, and here you can see the RIMS, the research, also known as the Research Institute for Microwave and Millimeter Wave Studies, located here. So this institute, in this campus, basically we are planning to hold the first international conference on microwave antennas and circuits, also known as ICMAC 2021. Why I say this first? Because this will be the first dedicated conference on RF and microwaves in Pakistan, and we hope all of you will join us in Pakistan next year to present your talks. So talking about the RIMS, we at RIMS is a dedicated postgraduate institute that offer MS and PhD programs in electrical engineering with a particular focus on RF and microwaves. We have very good faculty members that have international experience that teach the student. In addition, we also have the state-of-art research facilities. We have the anechoic chamber that works up to 40 gigahertz. We have EMC MyLab that is basically used for electromagnetic compatibility, pre-compliance testing, and also used in the course. We have the micro research and antenna lab, and also an in-house PCB fabrication facilities. All these facilities are available under one roof. This gives the student a chance to not just study theoretical concept, but also fabricate a design and also test it under the same platform. So as part of a webinar series that we have initiated back in March 2020 when there was pandemic lockdown, this is our webinar series talk number 10, in which we are very pleased to host Professor Francesca Vipiana from Department of Electronics and Telecommunication at Politecnico di Torino, Italy. The event title is Innovative Applications in Health and Food Industry through 3D Microwave Imaging and Sensing. A brief biography about Professor Francesca Vipiana. She received the Laura and PhD degrees in electronic engineering from Politecnico di Torino, Italy in 2000 and 2004 respectively. Her doctoral research was carried out partly at European Space Research Technology Center, Norway, the Netherlands. From 2005 to 2008, she was a research fellow with Department of Electronics, Politecnico di Torino in Italy. From 2009 to 2012, she was the head of Antenna and EMC Laboratory at Istituto Superiore Mario Bolia, also known as ISMB, that is also located in Politecnico di Torino. Since 2012, she has been an assistant professor at Department of Electronics and Telecommunication at same university, where she has been an associate professor since 2014. She was involved in the analysis, synthesis, and optimization of multi-band reconfigurable compact antennas and in the molding and design of microwave imaging. For the microwave imaging system are particularly designed for industrial application. Her current research interests include numerical techniques based on integral equation and method of moment approaches with a focus on multi-resolution scheme, domain decomposition, preconditioning and fast solution methods, and advanced quadrature integration schemes. Professor Vipiana received Young Scientist Award from Union of Radio Science General Assembly in 2005, the first prize in the poster competition from the first IEEE Women in Electromagnetics Workshop in 2009, the ISMB Best Paper Award in 2011, the Lutz Chopai Mid-Career Distinguished Award from IEEE Antennas and Propagation Society in 2017. She is currently the editorial board of the IEEE Transactions on Antennas Propagation and IEEE Antennas and Propagation magazine. We are very pleased to host Professor Francesca under this webinar series. And now I request Professor Francesca to please proceed ahead and start his talk. Over to you, Professor Francesca. Thank you.
Okay, thanks a lot for your very nice and kind presentation, and thanks for inviting me to giving this seminar. It's a pleasure for me. So now I try to share my presentation, and I hope to do it. Okay. Okay, so it's asking me more things. Okay, so should be this one. Okay, so now you should see the slides I put in presentation format.
Yes, everything is perfect, Professor. You may proceed. Thank you.
Works? Okay. Okay, so again, thanks a lot for the invitation. As already said, this seminar is focused on a technology that is microsensing and imaging, and I will spend the main time describing you not so much the theory, but focusing on a couple of applications we are working on in health and food industry. Then, as already said, I'm also more glad that today is the IEEE day, so I'm happy that I can give a seminar in this peculiar day, as already said. And before entering in the details of technical details of the seminar, I just would like to spend a couple of words about my university. That is Politecnico di Torino, that is in Torino, in the north part of Italy. Just a technical question, do you see my mouse moving or not?
No, I can't see your mouse. Can you please move it again?
Yes, I'm moving now. No, you don't see it. I tried to check if there is. Now you see red stuff?
Yes, yes, I can see now. I think it's working now.
Okay, okay. My university here is in Torino, as you can see from the map, is in the north part of Italy, close by France. And here I'm just reporting a few pictures of our campus, the main entrance, historical entrance for my university, all the new campus. And I just report few figures about my university that maybe can be interesting for the people that are listening to my talk. We have 160 years of history. We are the first engineering school in Italy, and we born in 1959 as Application School of Engineer. I'm reporting here some recent data about the foreign students that they are attending master studies in Politecnico, and they arrive from 115 different countries, and I would like to highlight here that at the fourth place we have students from Pakistan. In fact, there is a significant number of students, of foreign students coming from Pakistan. And to give you some numbers, so 2 years ago in the academic year 18-19, we had almost 7,000 students that are not Italian. So comparing maybe to other Italian university, Politecnico is a pretty international university where many courses also are given in English, not only in Italian, and so it could be a good opportunity for studying here or to spend just 1 year through an Erasmus procedure. Okay, then just few credits for all the people that working with me on the topics that I will describe you. First of all, I would like to mention all my group and colleagues from Politecnico di Torino. And then there are Dr. Croc and Scapaticci and Bellizzi and Professor Tedeschi from Napoli, still Italy, from CNR and the University Federico II in Naples, that we collaborate a lot on the topics that I will describe you. Then we have also collaboration, contribution from Yakimowicz and Duchesne from Paris, from CNRS and Central Superlect. A collaboration with Amélie Littmann, still from France, but from Marseille, from Institute Fresnel. And a collaboration with Laura Farina. She was previously a postdoc student in Politecnico, and now she's at Galway in Ireland. Okay, so really starting my seminar, as said, I will talk to you about microsensing and imaging. The key feature of this technology is that through microsensing and imaging, we are able to exploit differences in dielectric properties, where the dielectric properties, I mean complex permittivity. And here I report an example of a generic system that use micro-imaging, and essentially the general way to realize a system is to place the antennas, that here are just represented by the end of the coaxial cables, all around, usually on a circle. The object under analysis, in this case, is a breast, and the aim is to detect a scatter within it. In this specific example, this is a system developed for detecting and localizing a tumor within the breast. So the general behavior of this system is that all the antennas around the object under analysis, they act as transmitter and receiver, and we can, so they switch, so all of them are receiver and transmitters, and the signal received is then elaborated through proper imaging algorithm that allow you to reconstruct the position, the shape, and possibly also the material of the target that we are searching, in this case a tumor within the breast. So the key quantities that the microimaging system has to measure are two main things, are the incident field, that is the field that is radiated by the antennas, in this case just one antenna switched on, that is where you see the peak, the yellow peak, in a reference scenario. So in a scenario where the target that we are searching is not present. And then another field that is usually called the total field, that is the field radiated by the same group of antennas in the scenario where we are searching for a target. As you can see here, this total field is identifies something in front of the antenna, in fact is modified with respect to the incident one. So the real information that we need to have is the so-called scattered field, that is the difference between the total and the incident, and essentially is the field due to the presence of the scatterer. as you can see in this picture on the right. And as you can see, even if here there is not a color bar, but the scatter field is much lower in magnitude with respect to the total and the incident one that are measured. Moreover, it's important to highlight that ideally we would like to know the total, the incident field everywhere in within the object that we are analyzing. In reality, we know it only where we can place the antennas. So the receiving antenna giving us an information related to the field. And so essentially, if the antennas, as before, they are placed around the object under analysis, we know the field only in a few locations where we have the receiving antennas. And so as you can imagine, with this limited information, we need a pretty advanced signal processing technique in order then to extract the information about the possible presence of a target. Okay, so why people are interested in this technology? I try to list here some important attractive characteristics. First of all, it is a non-destructive technology, so the antenna are close by the object under analysis, but there is no changes in the object, as well as is a contactless technology, so there is no contact between the antennas and the object under analysis. Is safe, in particular if you compare with techniques based on X-rays. So in this case, we are using microwaves at very low power. To give an idea, it's similar to the power that is used for your the mobile phone, so is low power application. Is potentially real time. This is strongly related to the kind of imaging algorithm that is used and also the platform where the algorithm is implemented. Is expected to be cost efficient, mainly because we are working in a microwave range that is used also for several other applications, in particular for telecommunication applications, and so are already available transmitter or receiver used for other applications. So at the end of the story, the cost is very low. And then easy to operate in the sense that at the end we have an image, and so the operator can look at the image and decide based on the specific application. As all technology, we have also some intrinsic constraint or limitations. We have to keep in mind which is the spatial resolution and penetration depths of our system. Ideally, we would like to have a very high spatial resolution, at the same time a very high penetration depth. To increase the spatial resolution, one well-known technique is to increase the frequency, but if we work at high frequency, usually the material where the waves are penetrating in, they have higher losses, and so we reduce the penetration depths. So we have, once we design a system, we have to find a compromise between spatial resolution and penetration depths. And then another intrinsic constraint is the dielectric contrast. So as I said before, the system, the technology works if there is a difference in terms of dielectric characteristics between the target that we are searching, as the tumor that I was mentioning before, and the materials, in that case, the human tissues that are around. So we need to have this contrast. If this contrast is not present, if at the frequency where we are using the system, we have the same or very similar dielectric characteristics, the technology is not able to identify the target. Okay, then I try to summarize here the main ingredients to keep in mind if you would like to design a microimaging system. First of all, we need a problem-based design procedure that is specific to the application that we have in mind. Then you need a reliable and effective forward solver, also called a direct solver. So we need a good software able to model what then we are doing through measurements, and so to predict what should happen in measurements, also to help in the design. Then we need a model-based imaging technique. This is a key part of the system. So once we have all the measured data, we need a specific and model-based or related to the specific application imaging techniques allow them to generate the images. And then we need specialized hardware, the sense that in particular, if you, for example, if you want to accelerate your imaging technique, you can maybe implement that on FPGA. So you have to think also which are the specific constraints of your application. And then we have to keep in mind that the design and then the realization of the system should be devoted to a specific need. So what I mean is that are already available several imaging techniques, even if in health topic, as I will talk later. And they are already available on the market, used in the hospital. So is, I would say, impossible to propose a new technique that is covering a need that is already covered by other well-assessed imaging technique. So it's important to identify a need that is not already covered or well covered by available imaging techniques. And so there we can think if microimaging can fill that specific gap. Okay, as I said, I will focus not so much in theory, but in real-world application related to projects we are working on. The first one is about, the first topic is about quality control in food industry, and in particular the need where we design a system and we apply microimaging and sensing is the detection of foreign bodies contamination in packaged food product. And the other application is instead in medical diagnostic, and in particular, the need is the possibility to have a continuous monitoring of patients after the strong onset. So I will start with the first application in quality control food industry. As said, is the detection of foreign bodies in packaging products. As foreign bodies, I mean, as is here in the picture, plastic fragment or glass fragment. This is still an open issue in food manufacturers. Here I just reported some recent EU website about contamination through plastic or glass fragments. And this is the main reason of customer complaints against the manufacturers. And this can generate to the producer a loss of brand loyalty as well as large recall expenses. So which technique are already available for inline monitoring and inline detection? So what I mean is inline means that the imaging system is placed along the production line, along the packaging line, without taking out the product from the line. So the first three highlighted are the three already available on the market, already available when the manufacturers that produce food, packaged food. They are metal detectors that I think everybody knows. The obvious limitation of that is that they are able to detect only metals, so conductive materials. Then there are machine based on X-ray imaging. Currently, they are the best with the one with best performance right now. And anyhow, they have some known limitation, in particular in the capability of detecting low density plastics and thin glass. And this is a problem because the plastic that is used for the packaging, and is many times the ones that in little fragment could be inside the food, is a low density one. And then another technique instead is based on visible near infrared imaging. This works essentially for verifying the external part of the packaging, because with these frequencies we have a very limited penetrating lens, so it cannot be used to check if there is something inside the packaging. Then other techniques that are more at research levels and not already available in production lines are terrace imaging, that again, this is powerful, but is right now pretty expensive, and again, limited in penetrating lens. Ultrasound imaging, this is also another technique under research development, but the main practical limitation that we need a contact between the transducer and the object, and the object that in this case is the packaged food is moving very fast along the production line, so the contact is a problem. And then thermal imaging. And again, here the main limitation is that many times if the contaminants are, for example, glass or plastic, the variation, the thermal variation could be very low, so maybe not enough to identify the possible fragment. So this is just to give you a clear overview of which are the current imaging techniques, and so to demonstrate you that there is room for a new technique, that is what we are working on based on microwaves. Again, it's important to focus which are the main features of the application, and I try to list the main here. So here is a picture of a production line from an industry in Utkau we are working with, and this is an example of a line, production line, and this is a long belt, and the movement along the belt can be very fast. To give an idea, for this production line, that is a production line of cocoa cream, the velocity is 50 centimeters per second. If it's a production line that is the production is, I don't know, a bottle of glass, a bottle of water, the velocity is 100 centimeters per second. So we need for sure to make very fast measurements. Then the product in many parts are along a line, as you can see in this picture. So we cannot put in an easy way at least all the antennas around a circle, because the product are moving and we would like to do an inline monitoring. So while the product are moving along the line. And so for sure we have to consider aspect limited measurements. And then as you can see here, there is a lot of metal. The guides, for example, here you can see they are metallic. And you know the strong interaction between microwaves and metal. So it's important to consider that in the model. It's also possible to replace them with the plastic ones. This is already done inside the metal detectors, but anyhow, this is something that has to be considered. Okay, so which is the basics of the system that we developed. Essentially, we have a product moving along the line. In this picture, you see from the top, and we have just two antennas on the two sides, one transmitter and another receiver. Then we can switch between transmitter and receiver. And what we do, we take several measurements at different time instant while the product is moving along the line. This is fully equivalent to have the product not moving, as is here in the second picture on the right, and then a sequence, an array of antennas on the two sides. So in this specific application, we don't have already an antenna array, as it was in the initial example that I gave you, but we have just two antennas, and this becomes somehow an array considering the movement of the object. Then another important point is that we expect a very small perturbation in a scenario. In this case is the jar, where maybe inside there is the cocoa cream, that is instead well known. So considering that what you expect could be just a fragment of a plastic, so a small perturbation, this justified the choice to use the so-called differential imaging, where essentially where we are searching is just the change between a well-known scenario, so the standard product, and the perturbed one, where there are just a few changes, even if in the field within it, due to the possible fragment. So these allow to simplify a lot the inverse problem. So we can linearize the problem using the well-known distorted Born approximation, where essentially in the equation here that is put in relation the measurement scattering parameters and the problem that we are trying to solve, we consider that the total field within the region of interest, so within the jar, can be approximated with the background field, so the field that is present in the reference scenario, because the perturbation is very small. So what is reported here, so is our reference, the model of our problem, where I would like to highlight what we would like to find, that is this delta C, so the variation of the contrast. So essentially we identify where there is a dielectric variation between the reference scenario and the perturbed one. So essentially we identify the fragments that are present within the object. Then here there is the integral operator that is known, can be evaluated numerically. And then here on the left, we have the data that we are measuring. So essentially, for each pair of antennas, in this case, for each different time instant, we measure the transmission and reflection scattering parameter once one antenna is transmitting and the other is receiving. Here you see a delta because we have to make this measurement for the reference scenario and for the perturbed one. Thanks to the Born approximation, this is now a linear operator, as you can see here in a compact way, applied to the variation of the contrast. And so essentially, right in a bit more compact way, what we know, what we measure is at the antenna location, the differential scattering parameters. What we want to find is the variation of the dielectric of the contrast. And so essentially we have to invert this linear operator, that is a compact one. And to do that, we can use the well-known truncated singular value decomposition scheme, where what is needed is to evaluate the SVD of the operator. This can be not, I mean, a pretty heavy operation, but the good thing is that this is done on the operator that is related to the problem that where we are applying microimaging, but is not related to the specific measurement that we are doing in line. And so this is something that is done previously offline and just used in real time once we are making the measurement along the lines. And essentially what is done here, we try to reconstruct the variation of the contrast through the right, as you can see in the last equation, right singular vectors of the SVD of the operator, and we found the coefficient just projecting the measured differential scattering parameter on the left singular vectors and then normalize with respect to the singular value. So this operation is the one that has to be done online, but is a very fast operation, so is longer the measurement time. This is really like less than a millisecond, so if well implemented. Okay, then a key point is to identify the frequency range. As already said, we have to make a trade-off. So we want to penetrate within the object. So it's better to work a lower frequency because we have lower losses. At the same time, we need to identify the object. So we need to arrive to a specific resolution. And so on this other side, we need to work the higher frequency. And moreover, if then we want to realize, maybe commercialize the product, the system, we have always to keep in mind that everything, the control electronics, the complexity of the system, all the costs are lower if the frequency is lower. So to identify the frequency, then we have to focus on a kind of products. As I said, we are working with nude cows, so we focus first on this cocoa cream that essentially you can see here the relative dielectric constant, the conductivity. This is essentially an oil. In fact, is the main part is oil. And here give you an idea. So we have in the range we plan to work, so between 1 and 20 gigahertz, so we are around 3 as relative dielectric constant. This is the conductivity. The losses are not particularly high. Then below, I just reported the wavelength within the cream divided by 4 to give you an idea of the achievable resolution that we have, and the penetration depth. That, as you know, is we have always to keep in mind to be sure that the signal can penetrate from one side to the other side the object. And then summarizing and keeping in mind all these constraints, our choice was to work at around 10 gigahertz, where we have a penetration depth of 3.5 centimeter. The size of the jar is around 7-8 centimeters, so it's reasonable. And the lambda within the cocoa cream divided by 4 is 4 millimeter. Here, the minimum size object that we should be able to find is around 1-2 millimeters. But we have to keep in mind one specific comment to this application, that what we want to find is the location of the object and the presence or absence of a fragment. If we reconstruct an object a bit greater than what is original, so if it's 2 millimeters, we reconstruct as 4 or 5 millimeters, this is not a big issue because the industry is interested to know if something is inside and where. So it's not so important the size as, for example, instead is very important in health application. Okay, going a bit more in details about the system design. I already said about the frequency. This is the jar that is 8 centimeters. We assume to have a separation of also 8 centimeters between a jar and another jar. This is pretty common along the line. It's also a request, for example, for X-ray systems, so something that can be done. The velocity, as already said, is around 50 centimeters per second. And so with all this constraint, we plan to have a measurement for a length, a physical length of 12 centimeters, and to take 13 measurements along that physical length of the line. And this corresponds to a measurement time per jar that is a quarter of a second. And we can evaluate the sweep time. So the time that we have available for one measurement, one transmission parameter is 10 milliseconds. This is feasible with a medium level network analyzer. Okay, here there are some first results for 2D tomographic imaging. So here we are just simplifying the problem as a 2D problem. Here is the reference scenario. We apply the SVD that I already explained, and what you see here in the middle is the image that we get. We can notice that we are able to identify the position of the two fragments, 2 millimeter plastic contaminants, but we have some replica along the vertical axis here. Why that? This is somehow expected because in this simulation the product is moving along the horizontal line, so it's equivalent to have two arrays here along the x-axis, and we have no antennas along the vertical line because we can't put them there because the object is moving. And so we have a downsampling along Y. The result of that are some replica in the reconstruction that, again, due to this specific application, is accepted by the industry for the final application. Then here I just report the same result using projection on the right singular vectors, just to show that if as coefficient we use the projection of a known differential variation of the contrast, we get more or less the same result. So this means that the algorithm is working well. Then I move here to 3D, still simulation, but using realistic antenna. So this wideband horn antenna. I don't spend time in describing you the setup because it's essentially the same that I described at the beginning. And here we have some result. In the top, we have the known situation. So yellow is where there is the object and blue is the cream. Here we are able to have a 3D image. So I'm reporting the three main planes. We can look first in the second column, where is the same view as a 2D view. And you can see that we are able here to identify, in the picture below, there is the reconstruction. We identify, is the yellow spot, the position of the object that we are searching. In the other plane, in particular, we can look to the last one, the last column, we see a replica. Here we can also see, depends on the near field of the antenna, we can also see a cylinder, because essentially in this plane, the one shown in the last column, we have just one antenna, so we cannot focus. So with this system, we are able to see the position of the object in the XZ plane, but not in the vertical plane. And the other picture is just the combination of the other two. Then I shown here the same result using only bistatic measurements, so essentially using only the S21, S12, not using the reflection coefficients. You can see that it's still working, but we don't see on which side is the object. So if available, it's better to use also the reflection coefficient. This anyhow can be problematic in measurements because the two antennas, even if they should be identical, they are not. And so proper calibration are needed. And again, thinking about this specific application could be convenient not to use the reflection coefficient. Then this is the first measurement system. This is in our lab within an echoic chamber. You can recognize the antennas. And here this wood stuff here represents the line. As you can see here, nothing is moving, so the jar is moved by us. So for sure we have an inaccuracy in the relative position between the antennas and the jar. And also we put the fragment inside, but then this is a cocoa cream, so we don't see exactly where it is. So it can be also some inaccuracy in where we expect to find the contaminant. Anyhow, one more thing, just to underline why we are using only bistatic measurement. These two for different position are the S11 and the S22 of the two antennas. The two antennas should be identical. They are the same kind of same antenna, horn antennas. But you can see here that the S11 and S22 are pretty different of several dBs. So this is the main reason because we are not using this data then within the imaging procedure. And here there are some results, same visualization as in the simulations. Here instead are measurements with the system that I quickly show you. And you can see again, in particular in the second column, that we are able to identify the position and the presence of the fragment. And it's also important to show you this other result. This is the case once we are considering two measurements of two different jars without any contaminant inside. And ideally should be nothing. And you can see here that there is a bit of noise, but the level is much lower than the case once the contaminant is present. And this is very important for industrial application because the industry would like to discard only the jars that contains something. Okay, then we investigate also other parameters, not only that could be somehow complementary to imaging. In particular, I can focus here on the correlation. So essentially what we did, we considered several measurements. In the blue case here is two measurements of average measurement between cases where there is nothing inside. So essentially the measurement should be exactly the same. So we evaluate the correlation in position, so means that we have one frequency point and we consider the measurements at different position. The same we do also in correlation in frequency, so we consider one position and different frequencies. And what we expect? We expect a very high correlation, ideally 1, if we are making the measurement of the same condition. So an empty, I mean a jar without nothing inside, you can see that is high. If instead we have a contaminant, the two signals are not exactly the same, so we expect a lower correlation, as you can see here in the table or better in the pictures, where the red case is a correlation between an object with nothing inside, an object with a jar with a fragment, and the blue one is instead the case once we have two jars with nothing inside. Then last results about this topic, I would like to show you a first measurement campaign that we performed in Nutcao, so at the industrial facilities. Here we have really a moving line, as you can see from the slide. And as always, once you go to the real world, so this is a real production line, we have to focus on some issue that we didn't have in the lab. First of all, we clearly need a synchronization between the measurements and the movement of the line. What you see here in the top right are the measurement, the amplitude of the S21, when the synchronization is somehow done by hand, and this is always the same scenario. So you see that clearly there is no synchronization. We did a posteriori synchronization based on the maximum of this data. This is enough, you will see soon, to evaluate the correlations, but not enough for the imaging, because for the imaging we need also to know the relative position between the antennas and the moving jar. So for that we need a photocell. In fact, in the new system we are working on, we have a photocell that allows to synchronize the measurement. And then another issue is that you see that even if once synchronized, we have like a periodic ripple here. You can see also in this color picture on the bottom that is not related to the jar, because the jar is already far away from the antennas. And so we realize that this is due, even if the moving line is plastic, there are some metallic join that connects the different part of the lines, and our antennas are able to see them pretty well. So this is somehow a problem, because this is a moving part. So if it's not again well synchronized, we cannot cancel that noise and somehow due to this join. And so essentially we have two solutions. The more practical one is to make them in plastic, as is already done once a metal detector is used. Here we can't change the line, so essentially we put always in the same relative position the jar and the line below it. Okay, so giving you some results here, I'm reporting some correlation, same meaning again as in the previous case done in the lab. Here you also see the contaminant. In this mission campaign, we consider a metallic contaminant and then two plastic fragments that are the fragment reported here in the top left. And again, we evaluate the correlation. Probably the best is to look to the pictures. That this is the first one is in position correlation, this is in frequency. The case without the fragment, so the correlation between a jar without nothing inside, another jar without nothing inside, is they are the blue line. All the other cases are for the metallic and the plastic contaminant. We can see that in this case, even if we have several inaccuracies that can be has to be improved, the highest correlation is still the one when there is nothing inside, and so we are able to discriminate the presence of the contaminants. And this just to show you in comparison what we did in the lab and what we did in the industry, we can see that the correlation, the red one, the correlation due to the contaminant has a very similar behavior. What is a bit lower is the blue one, also the average we can see, that should be ideally 1. And so this is mainly due probably to the practical inaccuracy that we have in this first measurement campaign, and we are currently improve them. So to quickly conclude this first part, I've described you a system for detecting contaminants in packaged food product. The next step, as already said, is an automatic synchronization. We also would like to investigate other quality parameters and also to make advantage of machine learning techniques, considering that with this specific application we can generate lots of measurement, so we can instruct a machine learning algorithm to automatically detect the presence of a fragment. Then, if you're interested, many details are in this paper that will appear this month in the Antennas Propagation magazine, a special issue for EM imaging for food. Then I move to the other topic. I try to be a bit faster than the first one because the time is going. And as I said, the other application is for the continuous monitoring of patients after the strong onset. So here we are talking about a medical application of microimaging, in particular to the monitoring of brain stroke. It's well known that brain stroke is one of the most common diseases worldwide. There are current very good imaging diagnostic methodologies. The two main ones are MRI, magnetic resonance imaging, and the computer tomography. They are used in hospital, they work well, very well. The point is that they cannot be used for a continuous monitoring of what is happening in the head of the patient after the acute stage. So the idea here is to have a device that is cost efficient, portable, so can be placed at the bed, that is giving an information through imaging to the clinicians what is happening in the head, if the stroke is reducing in area or if is enlarging. So probably something has to be changed in try to improve the situation. Okay, this is the general system, as already said. In this case, we have an array of antennas that are around the upper part of the head. So we need a switching matrix because each antenna will act as a transmitter and receiver. And then as before, the signals are measured by the vector analyzer, processed, and then we get the image. Again, we design a system, we have to set a lot of parameters. First of all, we have to decide the frequency. So to decide the frequency, that is around 1 gigahertz, we use previous works cited here, where essentially replicating the different tissues that are within the head is evaluated the transmission coefficient for different frequencies and for different matching medium. The matching medium, coupling medium, is a medium that is put around the head where the antennas are immersed in, that is studied in order to improve the penetration of the field within the head. You can see that we have two red spots here where the transmission coefficient is maximum, here around 1 and here at around 4 gigahertz. And our choice is 1 also because at 4, if we also consider the losses are much higher than 1, and so consider the dimension of the head is around 20 centimeters, the received signal at 4 gigahertz is very low and difficult to be detected. Then, as said, we have to place a limited number of antennas on the upper part of the head. Ideally, we would like to have a continuous surface where we measure the field. And so we have to decide where to place them, which is the orientation, how many antennas we want. In order to do that, we follow a pretty rigorous procedure. I will be fast now, the details are in this paper. And we consider different parameters in order to decide how many antennas we need. One is the discretization error and the other one is the condition number. Okay, the discretization error, as expected, we are discretizing the operator, so more samples, so more antennas we place around, lower is the discretization error. But this is true if we assume an infinite dynamic in the measurement, as it is in simulation. But in reality, measurements, so our network analyzer has a finite dynamic. So if we consider that in the discretization error, we see that we have an improvement, so these are the cross in the picture, in the error, but then after 40 number of antennas, more or less, so we have more or less no improvement. And even if we stop at 30, okay, the error is a bit better, but not so much improved. On the other side, if you look to the condition number, in the discretization operator, more antennas we use, higher is the condition number. And so from that point of view, to have a stable system, we prefer to have a low number of antennas. So considering all these factors, at the end, the suggested number of antennas is around 30. In our specific case, then we decide to put 24. That is also a good number in then building the switching matrix. Okay, then as before, here we use differential imaging. Why we are using differential imaging? Because what we are doing is a monitoring of what is happening to the head. And so essentially we want to measure the variation that we have in the stroke area, that is here in blue, from one time instant to another one. So again, consider that we are doing a monitoring, the variation is localized and is small. And so we can linearize the problem, as before, apply the distort bond approximation. And so also here we are doing that, and we use the TSVD in order to find the variation of the contrast. So where there is a variation in the dielectric characteristic between one time instant and another time instant, essentially to understand if the stroke area is enlarging or reducing. So this is the numerical model of our system. Inside there is the head with the different tissue, and around the antennas. As you can see also from this picture, there is the antenna, that is a pretty standard one, with a block around. This block around is the matching medium. So in our design, instead of using, for example, a liquid matching medium, that for a helmet is a bit could be inconvenient from practical point of view, we decided to use a semi-solid one that is like a brick around the antenna, that is very practical for then the realization of the system. Then to again underline the importance to use in this application a matching medium, here we are reporting the differential scattering parameter, so essentially what is in input to the TSVD in simulation, using the break, so using the matching medium or not using it, for the same distance between the antennas. You can see that for different cases considered here, the differential scattering parameters are pretty higher once we put the matching medium. And this is very important because if we have a higher signal, for sure is less noisy and too easy to then to invert it. Here I give also some example. This is some picture of the differential scattering matrix, so essentially what is in input to the TSVD algorithm for different frequencies, 1 GHz, where we work also the limit of the band, 1.5. You can see that essentially what happens is that increasing the frequencies, as already said, the losses are higher, so the differential scattering parameter are lower. And this is something that we have for sure to check because working of data that are lower than minus 110 dB with the medium also good network analyzer is something that is very difficult to catch without significant noise. So this is a clear reason because it's better to work at around 1 GHz. Here is the effect of the noise, still in simulation, just to show how much stable is the inversion algorithm due to noise. It is pretty stable. You see that for a signal-to-noise ratio 7 dB, where the matrix is seems to be destroyed, we are still able to see the location, the size of the stroke. And then now I move to the prototype. Here is just a picture of the whole prototype. You can recognize here the phantom, the head phantom filled with a liquid representing the brain. All these black blocks are the antennas together with the matching medium. And this other stuff here is the switching matrix that allows to connect the 24 antennas to a pretty standard two-port network analyzer. And everything is controlled by an external program through a laptop. So this is switching matrix. We realized that using electromechanical coaxial switches, the choice of this kind of switches is to maximize the isolation and minimize the losses. In fact, considering also the flexible coaxial cable, we have a loss along each path of at 1 GHz around 1 dB. And this is the part of the system that allows us to have all the 24 antennas acting as transmitter and receiver. This is a few information about the antenna. If you're interested, there is a very recent paper where there are all the details. As said, the antenna is pretty standard. It's a printed wideband monopole embedded in this brick that is made of urethane, rubber, and graphite powder in order to have a medium with the relative permittivity of around a bit lower than 20, as we would like to have from the theoretical studies. And here there is the S11 of the antenna that, as expected, is well matched at around 1 GHz. We work usually between 800 megahertz up to 1 to 2 gigahertz. This is the phantom that currently we're using just one cavity phantom filled with the liquid representing the brain. These are the characteristics of the liquid. And these are some measurement results. The first check is using a target that is a spherical ball made of plastic in different location. And here there are the results trying to find the location of the sphere. First results here are performed using simulations, 3D simulation with our proprietary VM solver, and also adding noise. Without noise is working perfectly, and then we check what is happening, increasing the noise. This is still simulation, but using a sphere not made of plastic, but made of blood, so more realistic. And you can see that essentially we get the same results. The difference is highlighted here, that the differential scattering matrix is around 10 dB lower with respect to the one with plastic. This is essentially due to the fact that the contrast between plastic and the average brain is higher than blood and average brain, but obviously this is the case that we are interested in. And then now measurements results. Each column here corresponds to a different sphere location, also a different height. You see the matrix in the top, and below the reconstruction in one plane where the algorithm finds the maximum, where there is the center of the sphere. You see the sphere is pretty well detected. Here I'm showing just a video that is, because what we generate is a 3D image, and so here is showing the image at different levels, and you can see that the expected position in the top appears also in the reconstruction. And another way to visualize the result, it's here, where essentially we select all the points within the reconstructed imaging that is normalized to 0 dB from 0 up to minus 3 dB. And so these points in yellow localize the presence and the size, the shape of the sphere within the head. And then to conclude, just further simulation, we are currently going on in experimental validating the system. So these are newer simulations, measurements, where we put inside now a plastic bag with a liquid that is the same as blood, as microwave frequencies. And again, I'm showing you the reconstructed imaging where you see appearing a yellow spot where there is the location of the object that is representing the stroke. And so to conclude also this part, I try to describe you the design, the realization, and I said that we are ongoing in experimental validation of this microimaging device for brain stroke monitoring. Which are the next steps? We are in the middle of our measurement campaign, and you have seen results with homogeneous head phantoms. The next step is with the inhomogeneous head phantoms that inside we have the different tissues, so that this is obviously closer to reality. And also we are improving the hardware part in order to move from a prototypal device, as you have seen in the pictures, to a wearable helmet where we have flexible antennas that can be placed around a head. Again, here I'm summarizing the main references. In particular, the first two contains much more information with respect to what I had time here to describe you. So if you are interested, you can have a look to them. And to conclude, I've just to mention the sponsors of all this work. So the project Meat Food that is funded by Compagnia di San Paolo, about the food application, this European grant for the project Emerald that is instead about the health application, and two projects from our Minister of Education, University and Research, Mibrascan, that just finished about again health application, and Best Food that is instead about the application to food. So this is the end, and I really thank you for the time, and I'm available to answer to any question.
Thank you, Professor Francesca, for your very interesting talk. Now I will ask you questions that are available in the list. So the first question is about the antennas. What kind of antennas are used in the setup that you have mentioned?
Okay, so you still see the slides, huh? Yes, right?
Yes, yes.
Okay, so I move, I don't use the presentation, I can just move. Okay, so for this health application, the antennas are here. So first of all, we use an antenna that is a omnidirectional antenna. This was a first choice because essentially you have two options. You can use a directional antenna like a Vivaldi that is used in some systems that are still for microimaging, or an omnidirectional one like this one that is a monopole antenna. The radiating part is essentially this triangular part here. This is just the feeding with the matching. Why our choice was for an omnidirectional one? This is in the view first to minimize the number of antennas that we need around the head. If you have a directional one, for sure you have a higher gain in the specific direction, but essentially you want to cover the whole head, so it cannot be parts that are not well imaged due to this application. And minimizing the number of antennas is a big issue because also from a practical realization of the system and also for the final cost. So this is one great big reason because our choice is essentially a wideband monopole antenna printed on. This is dielectric. Here is just a standard FR4. So nothing. The other side, maybe you see it. There is the ground plane. Another point is that you put the antennas around the head, and as you can imagine, the head are different. So not all of us they have the same head. And if the antenna is very sensible to what is in front, so to the skin, to what is the external tissue of the head, this can be problematic because maybe different head can change the resonance of the antenna, and so the system is not working as well as expected. And if we use a omnidirectional antenna, usually the near field of the omnidirectional one is less modified by what is in the very near field of the antenna with respect to a directional one. So this is one more reason because we prefer to use a omnidirectional one. Obviously, the drawback is that is radiating everywhere. So if you look to the specific direction where the directional one is the design maximum radiation, we have a bit lower radiation. Instead, the other application, the food one, we use, at least in this realization, we use pretty standard antenna. These are two horn antennas, the one that we had in our anechoic chamber. And so here, I mean, is the part to be radiated is relatively small, then it's also moving. So we have not some issues that instead we need to have, we have for the health application. Moreover, here we have no problem of space, so we put the antenna close to the line, so it's not, we don't need something portable like a helmet. So we use standard antennas in this case.
Okay, thank you. The next question is about the imaging techniques. So you discussed about imaging techniques for tumor and cancer detection, but can you please also comment on diabetes? Is there any work going on in the area of diabetes?
In the area of, can you repeat?
Diabetes.
So no, I don't understand.
Diabetes is I don't know. Can you hear me clearly?
Yeah, more or less. Yes.
The question is regarding that microwave and imaging techniques used for tumor and cancer detection in biomedical.
Yes.
But can you please comment on the research going on in the area of diabetes cure?
So in the area of applying microimaging and sensing for tumor detection, you mean?
Yeah.
Yeah. Yes, this is, I mean, the detection of tumor inside the breast is the first application from what I know of microimaging in the health topic. In fact, my first example, I also worked at the very beginning on that with another project. My first picture, just showing you how it's working the general microimaging system, was from this paper that is microtomography for breast cancer.
Excuse me, Professor Francesca, I can't see your slide moving. It's still on the last slide.
I don't know. You see, maybe now.
You can exit the.
Maybe I exit the presentation. Yeah. Because also also the voice is not okay. Now I'm not presenting, so you see just my face, right?
Yes.
Okay, so I don't need the slide to
okay.
So it's better because I listen better. So essentially, the first, probably most famous application of microimaging and sensing, in particular in the health topic, is for detecting breast cancer. So this is lots of people who work on that. I also worked a bit years ago on this. This is for sure an interesting application, also because is a part of the body where it is easier to enter for microwaves. So this is probably, I imagine, the reason, because people started from there. And there's also a kind of pathology where if you have a non-invasive technique, low cost is for sure of interest. The main point that is somehow still open in devices that some of them are already on the market is that you really have the dielectric contrast. So as I said at the beginning, you need to have a dielectric contrast between what you search, the tumor, and what is around the tissues. And for the specific kind of the breast, if in some tissues is not so well demonstrated that you have a significant contrast. And so this is somehow, people are still working on that, limiting the wide application of the technology. In the case of the head, the contrast is sure, so we have a contrast also pretty high between blood and the brain. The point is that the penetration is much more different. So we have the bone that you don't have on the for the breast. We have a lot of tissues. So here the issue is to be able to really penetrate well, and so to have a signal that is not just noise. So this is the issue in these applications.
Correct. The next question is regarding the measurements that you have carried out. The question is the sample under test shall be in the far field of the antenna or in the near field also works fine?
All the examples that I reported are in the near field, or better in the very near field. So the distance between, I can show you the helmet, the distance, no, I cannot show because I can tell you. The distance between the antenna and the helm and the antenna and the head is, I don't know, 2 centimeters. So it's very, very in the near field. In the case of the food application is a bit more, is 5, 6, the frequency is also different, by the way. So anyhow, it's less in the very near field because we need to leave space for the movement. But in general, the application are in pretty near field.
So are these near field results are reliable results?
The data that we have in the near field, you mean? Yeah. This is what we have available. Yes, I can say we have enough information. What is better to avoid? The reason, because currently we are not putting the antenna touching the head, but there is still a gap of filled with a matching medium. Is that more than the data are there? The point is that is pretty difficult to model the behavior of the antenna once we are almost in contact with the antenna. And we need to do that because within our imaging algorithm or any other algorithm that one would like to use, you have to model the operator, so to model what is happening. In this case, we are modeling the scattering operator. And this model, numerical model that is used in combination with the measurements, has to be done as best as we can, because instead we introduce inaccuracies. And if the antenna is very, very close to the region of interest, is problematic. No, it's feasible, but problematic.
Right. The next question is that you talk about the TSVD algorithm.
Yes.
So are there any other algorithm choices that are available for food contamination imaging application?
Yes, we use the same algorithm for both applications. Essentially, the reason of that algorithm is due to the fact that first, we linearize the problem. So essentially, in both, even if the application is completely different, so there is no, somehow no connection between the food with a piece of plastic and the head with a stroke. But consider that in one case, we are searching for something very small, a fragment of few millimeters of plastic within a jar that is 8 centimeters side. And so we can assume that the variation in the field, the total field due to the fragment is very low. So this allows us to apply the Bone approximation to linearize the problem. And then we can use an algorithm that is for a linearized problem. So our choice is TSVD. There are other options, probably also good. This is the one that we like because it works pretty well. And it has the great advantage that the heavy part, so the SVD, is done offline. So then the part that you have to run with the measurements, so in the case of the food application, we must be very fast, is really something that if well implemented, you don't see it. So it's less than the measurement time, less than 10 milliseconds. So you essentially you don't see it. If you use another algorithm, for example, music, that I know I work with that, is still for linearized problem, but is doing the SVD of the measured data. So the operation of the SVD is for sure longer than what we need here. So we have this big issue of a fast elaboration, very, very fast elaboration of the data for the food. For the head, the time issue is less strong because, okay, we cannot wait 2 days, but if we need 1 minute, 2 minutes to elaborate the data is not a big issue. The total measurement time, to give an idea, is of the order of 5 minutes. So the total stuff is within 10 minutes. And so this is something that for a medical examination, even if with a prototype that is not optimized, is feasible. So in that case, it's not a so big issue, the time, even if we also somehow we are a bit expert with this algorithm, so we know also good things and bad things, and so we use it. But once we linearize the problem, also other algorithms can be used. It's not, I mean, this is not invented by us. We just take it and we apply.
Okay, perfect. The next question is regarding the experimental setup. So you have used VNA also in your experimental setup. So VNA is a very expensive equipment. So is there any other alternative options available if we don't use the VNA?
Yes, this is a good point, and I think that essentially there are 2 alternatives somehow. One is this is something that we did in a paper that is also for sure cited in the slide, so you can find it. The title is something like how to realize a VNA using cost, so pieces available on the market. And we did that specifically for breast cancer detection, but this part is common to all the devices. And so one option could be to realize the electronics, so not to use a network analyzer. This is something that at the end of the story, for sure, the object is less expensive than the network analyzer. It's just limited to maybe a specific frequency band, but this is what you need. On the other side, you need from I mean, your research point of view, a lot of activity to do it. So we prefer to focus on other parts. However, I would like to underline that currently there are compact, so VNA without any, just very small, like smaller than a PC, where there is no, essentially no software. Everything is done by the external laptop. And if, for example, in the case of the brain, where we work at around 1 gigahertz, one of these devices going up to 6 gigahertz, the cost is a few thousand euro. So with 4,000 euro, you buy it. So times ago, the network analyzer was always expensive. So we were used to talk about 50, 60, 70, 100,000 euros. So a very high cost. Now, if you have a limited band to work, and in particular if you work a low frequency at around 1 gigahertz with few thousand euros you have on the market, or on the other side you can realize it is we did it, but could be an issue, and now I mean we are focusing on other topics.
Yes, you're right. You have also used the switching matrix along with the VNA, for monitoring the stroke. So I think that switching matrix is also very expensive, if I'm not wrong.
Yes, okay. The switching matrix, we decided to realize it. So essentially, we bought the coaxial switches, and we did everything. So all the hardware part. Here, the cost is related to the characteristic of the switch, essentially. So less performance are required for the switch, lower is the cost. In this specific realization, we decided to take somehow the best available, because this was our first system realized, and we would like to reduce as much as we can all the inaccuracies that we can have around. So we decide to have a switching mechanism because we realize it instead of buying, because there are also some already realized with less performance. So in our case, we have an isolation of 100 dB. We have losses of less than 1 dB. So it's really incredible. So it's doing really as an ideal one. Then evaluating the performance of all the rest of the system, this now we know is a bit too much. So we have we could use much lower performance switches. We can use the one already realized. So it's true that the one that we have, if I sum the cost of all the switches, is expensive. So that stuff that you have looked, just the cost of the pieces is something like 20,000 euro, because it's a really high level one in performance. But I can say now that I have a system in my hand that is absolutely too much. So if now I will build another one, I will use probably the one already, not just the single switches, but already 24 by 1 switching matrix as lower isolation. And I'm expecting is working as well.
Yes, you're right. I think the custom-made system may reduce the cost. The next question is regarding the permittivity value. So what is the ideal permittivity value for coupling medium that represent the grain properties?
Okay, I don't show you, but it was just to recover for me to give you the coupling medium for the case of the health application, because in the other case we didn't use it. I would like to underline that we didn't use it for the food. Not because it's not needed, we would be happy to use it, but is almost impossible. So to have something moving along the line immersed in a coupling liquid is something that is unfeasible. So this is limiting a bit the penetration of the wave, but at the end of the story it works, and so we don't use it because it's not practically possible to do it. Instead, for the head is used. Also, the head is a bit more critical case, also because it's bigger, so it's 20 centimeter the size, and also very lossy, made of very lossy materials. So to improve the penetration is a key issue for a head application. And the permittivity and the relative permittivity that we use is at around 20. So what we would like to have is 20, and then is around 18. The choice of that is essentially related to the theoretical study that I shown during my presentation, where in that with that kind of permittivity for the matching medium, we maximize the transmission coefficient. So this is the reason of using it and the reason of that specific value. Then we have something a bit lower. This once we realize it, we have like this, but we can improve it more. So if you add in our specific realization more graphite powder you add, higher is the permittivity. However, you have two drawbacks. One, that at the same time is increasing also the conductivity. So you add losses close by the antenna. This is something that if you can, you like to avoid it. And moreover, also the flexibility is lower. So the rubber is very flexible. If you add graphite, it's still semi-flexible. If you add a lot, it's a block. And so we, again, is always a compromise. We reach almost the relative permittivity that we would like to have in our design, but keeping a realization of the coupling medium that is feasible.
Yes, thank you very much. I think we are done with the technical question. One generic question, not technical. Since you have a very good research profile and also you have a lot of publication in this area. So, as a woman, what is your message to the women in Pakistan to motivate them towards this RF and microwave engineering? I think on this IEEE day, I think you should give us some message for especially for the women in engineering. So how they motivate themselves towards engineering.
Yeah, this is a request that now is pretty common. Yeah, it's true that at least in our university, the reason at the end also because also at staff level we have less women than men is also because in the university we have less women, and so step by step, less are professor or researchers. On the other side, I always say that when a woman choose to learn and to study engineering subject, usually she is very successful because she's very motivated, because it's common in Pakistan, but also in Italy, that women should do something else. So they are not for technological material, so they should do or not working. That is also common here. I don't know in Pakistan, but I think yes, or doing other subjects, literature, history, philosophy, okay, something like this. So once a woman say, no, I want to study engineering subject because I like it, I think many women like it, so they may be a bit against what is the common message in the family, in the friends. They are very motivated and usually they perform very well. So once I have, even if a master student or for a thesis that is a woman, I'm sure that she's doing as best as they can. I'm not saying that all the men are bad, that is not true, but they are somehow less motivated. So what I do, hey, I try to study engineering subject, and just if you are not so convinced at the beginning, it's difficult to arrive to the end, or you are not so successful as you can be. So this is my message. So don't be shy if you like this subject, and then if you really like it, that could be very fascinating subject.
Yes, thank you very much. I also seen a trend that now more women are also joining the engineering field, and I hope to see more successful women in the area of engineering as well. So with this, I would like to thank you very much for your time and delivering this talk, and also would like to thank all the audience to join us on this IEEE day for this very useful webinar. And now I would like to conclude this session by thanking the speaker, and hope to see you in some other webinar as well. Yeah. Thank you very much, Professor Francesca, for your talk. Have a nice day. Bye-bye.
Bye.